All right, let's take a look at dynamic routing protocols. This is just an introduction to dynamic routing protocols. This is not to be an in-depth look into dynamic routing protocols, but just a brief overview. All right, first we'll take a look at dynamic routing protocols, what they are. Then we're going to take a look at distance vector versus link state routing protocols. We'll then take a little more in-depth look at distance vector and a little more in-depth look at link state to compare the difference between the two. Dynamic routing protocols is what routers use so they can discover remote networks. And so with this router right here, we know that this network is a directly connected network. And when you bring this interface up with an IP address and a subnet mask, then this network shows up in the routing table as a directly connected network. But how does it learn of this distant network, this remote network? Well, it's going to do that either by entering a static IP address where you manually enter that into the routing table, or it's going to learn it from other devices. And so other devices are going to share information so that way each one knows about each of the networks that exist out there. So that way communication can happen throughout all of these networks. So let's take a look at two common dynamic routing protocols, which one would be distance vector and one would be link state. Distance vector is made for much simpler setups and simpler designs versus link state is if you want some additional features. So distance vector is more simplistic in its setup versus a link state is more complex. But once you get it set up, link state has a lot more options to it than distance vector. So distance vector is commonly used for more simplistic or smaller networks versus link states are usually more for larger networks or more complex networks. So one of the things that we look at is path calculation and what it takes to calculate the path from one destination to another. So if a router receives a piece of information, how does it make it determine what is the next hop? And distance vector uses hop count. So the information that passes it around, and we're going to look more in depth into that here in a second, but the information that gets passed around just increments the hop count. So if it has a few routes that it could go to get to a remote network, and one of them has 2 hops, 2 other routers to get to that location, versus a path that has 3 hops or 3 different routers to get to that location, it's going to choose the 2 hop path, even if the bandwidth is significantly less on that. And so that's where we say distance vector is great if you have more simplistic, but if you have different bandwidths and different needs that you have more complex features, then distance vector is not going to be the right one for you. Versus link state uses what's called shortest path first, or shortest path metric, which it calculates a lot of different factors on how is going to be the best route, to include bandwidth. Bandwidth is a huge one that plays a factor into which route am I going to go. So that's shortest path metric with link state. There are some other information here. We're not going to get into it all, but some examples of this one would be RIP or IGRP would be examples of distance vector, and OSPF and IS-IS would be an example of link state protocols. So those are some examples of different protocols that fall within distance vector and link state. And one other thing to note is the algorithm here, Bellman-Ford versus, I'm not even going to try to pronounce that, but the algorithm here is just the process in which it chooses the best route to any kind of remote location, a remote network. So there's some differences between distance vector and link state. So when you actually look into distance vector, how is it calculating hop count? Well, we know that what this network right here is a directly connected network, And as soon as you bring up that interface with an IP address and subnet mask assigned to that IP address, that is going to go into its routing table. And so this also will have this router right here will have this directly connected network also within its routing table as well. And then these other devices, they still have networks that are associated with them. So here's networks in between each one of these, and those will all go into these routing tables. And so that information is found in the routing table. So now let's say we turn on something like RIP onto these routers, and now this information uses the RIP protocol to pass the information back and forth. And what that looks like is this routing table gets dispersed in both directions, and then these devices, provided that they have the same dynamic routing protocol turned on, will listen to that and take that information in and put that into their routing table. But when they put it into the routing table, they'll increase the hop count by 1. And then they will take their tables and disperse it in each direction as well. And so this information then makes it to this router right here. And that the information to this remote network then makes it into this routing table. Then this router is going to send information out, and that information is going to get into here, and then it will make it into this routing table right here. So then this remote network is inside of this routing table right here. So then what happens is this information gets passed back and forth, and all of this information gets put into these routing tables, and that's distance vector. But every time it gets passed from one location to the next, it increments that hop count. So this router right here understands it's 1 hop this direction to get to this network. It's 2 hops in this direction, and it's 3 hops in this direction. So since this is a distance vector dynamic routing protocol, it's going to choose the shortest path is going to be the least amount of hop counts, so it's going to be the straight line over to it. Even if this is the smaller bandwidth and has a lot less bandwidth, it will choose this location, this route, over the other routes. All right, now we have something called convergence. Convergence is the time, or is the aspect of all of these routers when they get the full view of all of the networks. Then we've reached convergence. There's a convergent speed in which the speed in which all of this communication happens. So this is what I mean by this, is let's say this router right here sends information to this router and this router. So it sends it out, and that information for these routes gets put into the routing table. This router still doesn't understand about this network right here. And so now what happens is this router right here sends out information in this direction and this direction, and this network is learned into this router, and then this router will then give an update out of both directions. So now that route gets put into here. So now this router knows and understands about this network, but still doesn't know about this network right here. And then this router sends out information in both directions. This router sends out information in both directions. This router sends out information in both the directions. And then what happens is that finally the route to this network finally gets passed on to this router, and this router understands that this network can be found in this direction. And so what we have is we have a learning process where all of these routers start communicating out. And as soon as they get an update, they communicate out again. And as soon as they get an update, they communicate out again. And that has to happen until everybody understands all of the networks and there's no more updates to be had. At that point in time, we've reached convergence. Convergence is the point in time when all routers on this particular segment here, all of these routers operating in RIP understand where all of the networks are at, and now we have convergence. The speed in which that happens is called the convergent speed, and the speed in which we converge, the network converges, and all of the routers get the full picture of how to get to each one of these networks. Some examples of this would be RIP version 2, IGRP, EIGRP would be all examples of distance vector. Link state has the same thing where all of the networks need to be converged, or the routers need to converge into one solid form or one solid map. And that's actually one difference about link state, where a router just understands what's the next best hop, what's the next hop where I need to send information. And it's very simplistic in the way it just transfers the whole routing table, gets sent out each direction, and that's how it reaches convergence. Versus link state's a little different. When a route gets added, it will form some information about that network that's been added, and then it will send out in each direction information about that network. And so this information, rather than the whole routing table, the information gets sent out, and the repercussions from that is that all the routers understand where all the connections are within this instance of the routing protocol. And so the information is passed all around, and each router can create essentially a map, an internal map of how all the connections are connected. And so it has a much more global view of how networks are, and if a link goes down, what other directions it can send information as a backup way of doing it. RIP and distance vector has some capability of doing that also, but it's just link state has much more able to adapt and adjust because it has the whole concept of the whole map of how the networks are arranged. And another difference with this too is as a link goes down, like let's say this network, this remote network to all these routers that are out here goes down, then rather than setting out the whole routing table to discover what the update is, it will just send out updates of what specific link went down. So once a network is converged, and convergence can happen possibly a little bit longer with link state, but once it is converged, then all it needs to do is send out little updates to update everybody on any changes that happen to this network. And so that's link state. And that's, as you can see, there's a lot more of little communications that happen for managing this type of network and to give little updates and stuff. And rather than these big communications of transferring the whole routing table from one router to the next. So it adds a lot of different features and allows for a lot of positive features, great features that can be added to link state over a distance vector routing protocol. All right, here's another breakdown of it. We talked about convergent speed here, and so here are some different aspects to how these different routing protocols and how fast they can converge, how scalable each one of these routing protocols are, the resource usage that each one of these routing protocols will take up, and resource would mean like how much compute power a router will need, how much memory a router will need, and how to implement and maintain. And distance vector, once again, for the most part, we see that it's simple to implement. It takes up lower usage from a resource standpoint, although convergence is slower. Scalability, it's not really scalable. Versus the link state, we have much faster convergence, but it's much more complex in implementing. Resource usage can be higher. But we also see this magic little spot right here, EIGRP. So from here, RIP version 1 and RIP version 2 would be the most basic implementations. IGRP gives you a few more features. EIGRP is Cisco's enhanced IGRP, and it takes a little bit from each of the worlds, and it's still not the perfect protocol, but it combines some of the advantages of distance vector with some of the advantages of link state, and we find a little bit of a happy medium ground with the EIGRP. All right, real quick summary about intro dynamic routing protocols. We talked about dynamic routing protocols and specifically around distance vector and link state. I gave some examples of some distance vector and explained briefly what distance vector is versus what link state, and how link state just transfers updates around rather than the full routing table. So great, thanks for joining me, and this has been Dynamic Routing Protocols. If you like this video, could you hit that like button?